And we're back. So the next talk already, and Dylan actually alluded to it already, this is a serious problem that Julia is tackling. So Julia is presenting joint work with Julian Manvi and Friedemann on optimal initialization strategies for deep SNNs. And I'm also very interested. This is very difficult. So Julia, please, go ahead.
Yeah, thanks. Yeah, I'm very excited to talk here today at SNUFA. As already mentioned, I want to thank already here to Julian, Manvi, and Friedemann, who were working together with me on this project. The question we want to address is today how we should initialize spike neural networks, as it is now possible due to surrogate gradients to do end-to-end optimization. This has become a bigger question. It is already known for general ANNs that a good initialization is crucial also for a good performance. Here an example from 2015 where with this init in ANNs, it was suddenly possible to train a network that with another initialization wasn't trainable at all. And for our case in SNNs, we take some inspiration from biology. Here you can see a spike raster plot where time is on the x-axis, and here on the y-axis we have the neuron indices, so each dot is a spike. This is here, in this case, asynchronous irregular firing, which happens due to being in this fluctuation-driven regime, where we have some excitatory input current, which is closely followed by an inhibitory input current, so that they nearly cancel each other in time. So if you look at the membrane potential, there are some random fluctuation with just occasionally emitting a spike. And we hypothesize now that this fluctuation-driven regime might be a good initial state for future learning. And therefore, so let's look at our neural model. We're using a leaky integrate and fire model, where we have this Poisson distributed input spikes, and then should lead to such a fluctuation-driven membrane potential. The equation that describes here with filters the behavior of this membrane potential, you can see here on the right. We are focusing now only in the sub-threshold regime, so looking how it looks like when a spike is generated from the input. So we have here the spike trains, so this input, that are filtered with this epsilon kernel that just describes the shape of such a spike, and then weighted with the synaptic weight. So the question is now, how should we choose those weights to really end up then in this fluctuation-driven regime? And first of all, we look how we can describe this fluctuation-driven regime. So if we just sum up all the values of the membrane potential into a histogram, we can see that this leads to this nice Gaussian distribution, with here the mean around 0, and we have the threshold at xi times the standard deviation. So with this xi, we can kind of vary the width of this distribution, so that we can specify how much of this tail of the Gaussian gets cut off as above the threshold. So those are then the values that will induce spiking. Here again, I put the part of the formula we're using now for the sub-threshold regime. And then we can now determine the values like the mean and the standard deviation of this distribution. And if we now make some assumptions for that the map gets simpler, we use n inputs with the same firing rate, and we also have independently identically distributed weights. And just for this talk today, we will stay at the mean membrane potential of 0, so that the expressions get a little bit easier. So if we now use these assumptions, we can simplify the expression for the variance. And now you already see that we have now a variance and mean of the weights in there. So we can solve this just for the variance of the weights. For the mean now, since we assumed a mean membrane potential of 0, also the mean of the weights have to be 0. Therefore, we choose mean of the weight 0 and the variance dependent on the number of inputs, the firing rate of the input neurons, and then we have the variance of this epsilon kernel again, threshold, and our psi that determines the distance between the mean of the distribution and where the threshold is. So we can say now we have found this distribution that when we sample the weights from here, we can finally end up with such a distribution in the membrane potential, so be in the fluctuation-driven regime. So now let's see how this applies to the experimental results. We had 2 classification tasks. First one is the random manifolds dataset, also called RANDMAN, which is a synthetic classification dataset with some temporal structure. And the idea is simply that we have this space of all spike times, here in the example in 3 dimensions. And there we put some random manifolds. From them we can then sample spike times. So each neuron then during the simulation time just spikes once. This could then look like this here. On the other hand, we have some real data. So the spiking Heidelberg dataset we took, which is spoken digits from 0 to 9 in both German and English. And they are already provided as spikes. So here you can see how such a sample will look like. Then we also had different kind of architectures, starting here with one hidden layer networks. This is a feed-forward network of leaky integrate and fire neurons. Then to be a little bit more biologically plausible, we add Dale's law with now 2 separated, like an excitatory and an inhibitory population. And we also added recurrent connections in the hidden layer that they are, of course, time constraints due to inhibiting neurons only inhibit. And finally, we had 3 hidden layer networks, which is now a spiking CNN. So let's start with the simple one. So here you can see a raster plot of, or like here you can see in the color the inputs colored corresponding to the label they have. Then there is in the hidden layer some nice activity, and then in the readout you can see the membrane potential of the readout neurons, where I just colored the one that corresponds to this label in the same color, and the others are gray here. We are using a maximum over time loss, so the one that is the winner should be reached once a maximum in this simulation time. And then after we trained this with surrogate gradient, it really is now the highest membrane potential. We made some parameter sweep over different standard deviations and means of the weight, where you can see here those black lines correspond to this initialization we derived before. And as you can see, the maximum value of test accuracies in our runs is really following this line, although as you can see, the absolute values of the weights should not be too big. So this example you can see here on the left side is taken from where the star is at a mean of the weights of 0 and the corresponding standard deviation after the formula. And now let's look also at one that is top here at the bad accuracy. So you can see that already at initialization, the hidden layer neurons just spike at every possible time. And also training does not really help. So this also might explain the bad performance of this network here. Then we're moving now to this Dalian network. Now you can see in the hidden layer, we have a population of inhibitory neurons, around 20%, and then 80% of excitatory neurons. And it turns out that this method also extends to such Dalian recurrent networks. What is also interesting in this case is now we can look at the behavior of the excitatory and inhibitory inputs. So if we now see The excitatory input here in blue is quite closely after some delay followed by the inhibitory input, and if they follow each other like at each time step quite closely, we can say it's tightly balanced. And if we analyze this balanced over different ones, we can see that the best performing ones, they all are rather balanced, although in all the not best performing ones, there are still some quite balanced networks. And therefore, we can conclude in this case that balance is indeed necessary for a good performance, but it's not sufficient. It turns out that also, for example, the activity could be interesting in case to predict good performance. Then let's go to the spiking CNN. So you can see here how this looks like before training. This is now on the SHD dataset, where you see the 3 different convolutional layer. Also trained with surrogate gradient, it looks like this after training. And as we already know generally from ANNs that deeper networks usually perform better than shallow ones. Also, this is here the case. So a 3-layer network performs, when looking at the test accuracy, performs quite a bit better than the single layer one. Although when we look now at a parameter sweep over Xi, we see that with one single hidden layer, we have quite a broad regime where the parameter or the initialization leads to good performance, while for the networks with 3 hidden layer, there is quite a narrow regime that we need to hit for a good performance. So deep networks require quite more precise initialization. This is when we look now at the network, like at this parameter here, we can see that the reason is that the activity does not even propagate to the 3rd hidden layer, and so nothing reaches the readout. So there is no gradient at all at the end that we can apply our loss to, so we cannot learn anything with this network. And if we now look at the firing rate over the different hidden layers here, for this case, you can see that already with quite a lot of this of parameter sweeps, we can see that at the 3rd hidden layer, we don't have any activity at all. And there is now, of course, the question how we can help or rescue this. So there is this firing rate homeostasis, where we could define a regime with acceptable firing rate where training works well. But if you go below here, for example, neuron doesn't spike at all, we can apply this per neuron lower bound homeostasis. So each neuron is required to at least spike once, otherwise this loss term is applied. And also we have something like this in the other direction, where when the whole population just fires too much, we have this loss that is applied, that tries to drive the firing rate again in this acceptable regime. Then when we look this in our experimental setting, so going back to the 3-layer networks you saw before with this quite narrow parameter regime that leads to good training, we can see that with firing rate homeostasis, we suddenly have a quite broad regime where the performance is good. So when you look now at the firing rate rates over the layers without homeostasis, you see that it doesn't learn anything. So before and after training just looks the same. While when we add some homeostasis, we can rescue this firing rate. So also the hidden layers show some activity now. Okay, now to sum up everything, we can say that in shallow network, our method works quite well to provide a good initialization, and best is when we also looked at the absolute value of the weights remain small, so maybe the mean at 0. For deeper network, it requires a more precise initialization, but the firing rate homeostasis might help there. And then we also saw that balance seems to be a good initial state for future learning. Now there is also some work in progress. For example, in the case of Dalian networks, we were using truncated Gaussians, which were truncated at 0 before, but one could also look more into distributions that are already truncated at 0, like the exponential or log normal distribution, and still are able to provide such a fluctuation-driven membrane potential. And we're also exploring more in different homeostatic initialization mechanisms, like, for example, against synchrony, or maybe as kind of driving a suboptimal initialization at a good point to start draining there. And also we're looking more in the effects of balance in Dalian networks. Now I want to acknowledge again Julian, Manvi, and Friedemann especially, but also the other people from the lab. And you find our web presence here in this box, and the code will be released on our GitHub, and also we're working on a preprint. Yeah.
Great, thank you very much, Julia. Very inspiring. So inspiring that I have to ask for a friend on behalf of Dan Goodman. Could you make the math also work for time constants? So basically the temporal dynamics, how they influence the membrane distribution?
The time constants are also included. Maybe I just switched to a backup slide I prepared here. So we have this epsilon kernel, and if we now do all the math and everything, it will turn out that the epsilon bar is exactly the synaptic time constant, where the epsilon hat is this part, like it depends on both the synaptic and the membrane time constant.
And you could make this argument also about the distribution, if you were to work with distributions of time constants.
We didn't yet work with distribution. We just had a fixed time constant for each population.
But then you would maybe need to average over these quantities here.
Yes.
Very, very cool. Nice. Thank you. A couple more questions. Jamie Knight is asking, how do you include the Dale's law constraints in the network? Maybe you can add a bit on that.
We were like, for the initialization, we were using just a Gaussian with mean at 0, where we just took the absolute value, so to have only positive weights. And then to initialize the network, we just took the negative soft plus function of this. And in every run, like in every update step, we first again apply the soft plus transform, so that there then only are positive weights, and they cannot get negative.
Clear. Jamie also has more questions. So he's wondering, and so am I actually, does better initialization also speed up our training? It tends to be slow, our current training. We were first like trying to focus more on performance, so trying to fix like some number of epochs where we then just look like the accuracy at the end of this. But we didn't really explore more on this topic. Or maybe Julian, if you want to add something.
Yeah, I can jump in quickly. Yes, I actually looked at this. It seems like the optimal initialization also speeds up training substantially. So in order to really compare especially in the deep networks, it does speed up training if you're at this like narrow parameter regime where it actually works really well.
Okay, nice. Good to know. See if we can use it. I think we can ask one more question. Memming Park was really early with a question regarding the fluctuation regime. He notes that it would be great for instantaneous responses. And he asks, could you comment on the effect on temporal memory properties of your initialization scheme? Do you suffer from vanishing gradient type problems?
Yeah, actually, it's rather more obvious in the deep network. So I would say this is a good example for where we had some vanishing gradient problem. This is where when we really are in our good initialization regime, also the spikes will propagate through till the end of the readout, so we don't have any vanishing gradients. But to be really sure that the performance works well, there's also this kind of loss that can be applied to work against vanishing gradients, because in this case every neuron is forced to spike at least once. So if there at the beginning would be any kind of vanishing gradients in the objective function, we also still have this homeostasis that would rescue this.
Yes,
I think on the point of temporal memory properties, this is a super interesting thought, actually. I think that because this fluctuation-driven regime initialization doesn't mean that the membrane potentials of individual neurons are some close to threshold already at the start of the simulation, right? So I'm not sure how this would be great for instantaneous responses. For longer samples, I guess you would have that, but in terms of temporal memory properties, I would rather argue that this would be in the time constants of the neurons, and that then that would link back maybe to generalizing this to heterogeneous time constants in the network.
I think we should keep it to this. Julia, thank you once again for a great talk, and I'm looking forward very much to the archive papers too. So we can also use it. And I propose we now switch to the next talk, which should be in 1 minute ago. So see you in a bit.